With Pgpool, we can build highly available systems that can continue to operate even if a failure occurs. In addition, we can achieve scalability so that servers can be added as the system responds to more and more users. In this tutorial, we'll see how to set up a solution for both requirements, high availability and load balancing. For this, we'll use Pgpool, which is one of the PostgreSQL open source extension. Pgpool is a middleware that works between the PostgreSQL servers and the database clients. First, let's shortly discuss the load balancing feature. Scaling out is one way to increase the processing capacity of the entire database system. We do this by adding more servers. Core PostgreSQL allows you to scale out using streaming replication or logical replication. Still, PostgreSQL itself doesn't have a distribution feature, but we can use the load balancing feature of Pgpool to efficiently distribute read-only queries. The writes will always go to the master server, but we can configure Pgpool middleware to balance selects over a number of servers. Also, it allows to assign weights to the servers so that we can decide how much load to send to a certain server. Still, we have to be careful with functions that change the data but are executed as selects. For this, we could look up the black function list from Pgpool to deal with the issue. Then, Pgpool provides connection pooling. Acquiring a connection always has a minor overhead attached to it. So, when we need to make thousands of connections, reusing connections is crucial to performance. For this, the Pgpool middleware provides connection pooling. Basically, it reuses a connection when a request for a new connection comes in that has the same properties. Also, there are parameters to adjust the number of pools as well as the number of connections in a pool. Still, if you are looking for a solution that provides connection pooling and nothing more, you need to look at pgbouncer. This is a much lighter tool to achieve connection pooling. Pgpool also provides automatic failover for the cluster. In the event of Pgpool detecting a failure on the primary node, it can execute a script to handle the failover. However, we have to write this script, but we can decide how to handle the standby promotion. Of course, the promotion can be done manually as well. Finally, Pgpool has high availability for itself as well. This is done so that Pgpool doesn't become a single point of failure. In order to implement high availability of the entire system, Pgpool itself also needs to be made redundant. The feature for this redundancy is called Watchdog. Nonetheless, when using Postgres in distributed configurations, we need to take into account the possible consequences. For example, split brains occurs when there is more than one master node available at the same time. In this case, we'll have different information on each node, and this generates data inconsistency in the cluster. We'll talk about some approaches to handle this situation. However, as we'll see, it's not possible to ensure both consistency and availability, and we'll have to prioritize one over the other. There is also a whole theory which extensively explains this, called the cap theorem. The easiest approach to high availability with Pgpool is to use PostgreSQL built-in streaming replication to sync the data, and then use Pgpool to do load balancing and automatic failover. The Pgpool tool can be configured to automatically send write requests to the primary node and read requests to the replica. Although Pgpool has its own statement-level replication, it's not very often used. Instead, it's perfectly fine to use PostgreSQL built-in replication and use Pgpool just for load balancing, connection pooling, and automatic failover. In fact, it can even be beneficial to do so because we don't have to worry about side effects or potential issues. The PostgreSQL transaction log is always right, and it can be considered reliable. The Pgpool replication was a good feature, but now that streaming replication is built into the core PostgreSQL, it's recommended to use that. Before we get started with setting up load balancing, read-write separation, and automatic failover, we have to set up the replication. We choose to do it via built-in streaming replication because it's easier to set up and it's reliable. Also, it lets the replica server to be promoted as primary in case of a failure. For a full presentation on streaming replication, check the video in the description. First, we need to create a new PostgreSQL instance as the primary node. For this, we're going to use the initdb command tool included in the PostgreSQL installation. So, initdb -d, and then we specify a directory where PostgreSQL will store all the data and all the configurations. The directory doesn't necessarily need to exist beforehand. Next, we'll configure the primary server for replication. To do this, we'll have to modify the PostgreSQL configuration file. So, nano, I'll use the nano tool to make the changes, temp primary.db PostgreSQL configuration file. First, we'll change the listen address parameter. Ctrl and W to search, listen address, and we uncomment this. By default, PostgreSQL only listens on the local host, which is okay for a tutorial, but for production environments, we might want to use multiple machines. So, we allow this server to listen to any connection. Next, since in this tutorial we'll work on the local host, we'll need to change the ports to avoid conflicts. We set it to 5433. And that's it. Ctrl and X to exit. It will ask if we want to save the file. Yes. And now, to start the database, we'll use the pgctl command. So, pgctl -d temp primary.db and start. The server started successfully on port 5433. The next step is to create a separate user for the replication. This step is optional, but it's best practice. We connect to the server, psql --port 5433, and the database is Postgres. Create user, rep user. Here, it is important for the user to have the replication flag set. Then, we'll modify the host-based authentication pg_hba configuration file to control who is allowed to connect to this PostgreSQL instance and from which IP. We copy-paste this line and then replace the user. Normally, you would set here the IP address as well. Then, we restart the server to make sure that the changes are applied. This is not really necessary since a reload will be enough. The next step is to create the replica. For this, we'll use the pgbase backup command. This will simply connect to the primary and copy all the files over to the replica. So, pg_base backup -h localhost -u rep user. The connection has to be made as the rep user. Then --checkpoint equal fast. This is to ensure that the copy process starts instantly, so it makes sense to tell Postgres to quickly checkpoint. Then -d to define the destination directory where we want to store the data to the replica. Then -r to automatically configure our replica. And finally, we create a slot with --slot. We give it a random name. And -c. This option is necessary so that the primary can recycle the wall files only after the replica has fully consumed it. Now, let's see what this command has done. In another window, we move to temp/replicadb and then we list all files. The configuration have been taken from the primary. Still, we need to change the port on the replica to avoid a port conflict. So, nano PostgreSQL config, we search for the port configuration and we change it to 5434. Now we are done and we can proceed to start the replica using pgctl. We see that the replica is now in standby mode, read only, and streaming replication is ongoing. Normally, while using the built-in streaming replication, the primary server will receive both the write and the read requests. Postgres itself doesn't distribute the read load unless we connect directly to the replica. So, in the first example, we'll configure Pgpool so that it sends the write requests such as inserts and deletes to the primary server and the select requests only to the standby server. First, we need to install Pgpool. Depending on your operating system, you can install Pgpool-II using your own package manager. For instance, I use Brew. Here you can use apt, yum, rpm, or any other package manager. Or you can download the sources and then build them. Since I already have the Pgpool installed, I'm not going to execute this command. Now, let's see the configuration changes we need to make to the Pgpool. The configuration parameters are found under user/local/etc. When we install Pgpool-II, a file name called pgpool.config.sample is automatically created. We can use this sample file to create our own configuration file. So, cp for copy, and then rename the sample file to pgpool.config. And then we can edit the file as we like. Inside the file, we have the same format with parameters and the value. First, the default replication method chosen by Pgpool is streaming replication, which we already set up earlier, so we'll leave it like this. Then, again, we need to change the listen address parameter. So here, we instruct Pgpool to listen on remote requests as well. For this tutorial, I could leave here localhost, but keep in mind that in real-life environments, you'll have to change this. Also, Pgpool-II accepts connections using port 9999. Therefore, we'll connect our client applications to this Pgpool instance using this port. Now, we need to let Pgpool know which are the Postgres backend servers. Keep in mind that the servers can be placed within the same host as Pgpool or on separate machines. If you decide to place the servers on the same host, different ports numbers must be assigned for each server. Else, if the servers are placed on separate machines, they must be configured properly so that they can accept network connections from Pgpool. In this tutorial, we will place two Postgres servers within the same host as Pgpool, and we assigned the port numbers 5433 and 5434. So, let's configure the backend databases where we want to distribute the load. The backend with number 0 is treated as the master, and the backend ending with 1 is the standby. As we are using streaming replication, we can have only one master. We'll see later in the logs how SQL client requests will refer to this number. First, we set the host to local. Then, since we started the primary instance on port 5433, we set it here. Then we can decide the load balancing ratio by setting the weight. Here, let's set the value 0 for the primary and the value 1 for the secondary. This means that select queries will always go to the standby. Normally, the weights should be adjusted considering your own use case based on the number of nodes and similar factors. For example, if you have 3 nodes and set the weights to 0, 1, and 2 for the node 0, node 1, and node 2 respectively, 0 select statements will go to node 0, about 1/3 of the select statements will go to the node 1, and 2/3 of the select statements will go to node 2. Then, we have to set the directories where the backend databases reside. In our case, temp primarydb. Then, for the replica server, we have to do the same. Set the host to local, set the port to 5434, the weight is 1, and the directory of the database is temp replicadb. Then, we want to turn on the logs to see how the requests are distributed. We search for log underscore statement and also the log per node statement. However, these kind of logs should be turned off in production. Ctrl and O to save the changes. And for this tutorial to work, I also need to change the PID file name to be relative to the installation. Then we set the streaming replication user to the user we created previously. Finally, we set the health check to run every 10 seconds, and the user will be the one from the streaming replication. To fire up Pgpool, we can simply run the Pgpool command. However, this command doesn't print log messages. This is because Pgpool is run as a background process and the terminal is detached. If we want to show the Pgpool log messages, we can pass the -n option to the command. This way, Pgpool will be executed as a non-daemon process and the terminal will not be detached. Still, we don't want the command to run in the foreground, since we'll run other commands later. So, we add the end symbol at the end. Now the log messages are printed on the terminal. We see that the Pgpool has detected the master and the standby servers. Now, let's see how the distribution works. In another window, we open a PSQL session and we connect it directly to Pgpool. PSQL -p, that is the port 9999, and the database Postgres. Then we execute a couple of SQL commands, create table, table1, with a column ID as integer, insert into table 1 values 1, then select all from table 1. We see that the insert statement went to node 0 and the select statement went to node 1. Now let's do a delete. Delete from table 1 and execute another select and see how Pgpool is handling this. Again, the write statement went to node 0 and the read statement went to node 1. Still, in a production environment, It would be better to store these logs in a file to see them later. For this, we stop the pgpool and we start it with some other options. pgpool-n. Then we redirect the messages to a file which we can call pgpool.log. And we want to redirect both the error stream and the standard output stream to this log file. We do this by adding the number 2, which is the standard error output. Then we redirect this to 1, which stands for the standard output stream. And finally, we add the n symbol to not run this in the foreground. This command will keep adding log messages to the pgpool log file. We can check it via the command more, and then we specify the log file. Before diving into the high availability subject, we must be aware of some of the troubles with distributed systems. One such issue relates to how we should handle the failover. In the event of a failover, when the primary or the master is lost, any transaction committed on the master that was not already synced or applied to the standby could be lost. So, in this case, either the application should be designed to handle such situations and apply any lost transactions, or we must wait until the recovery is completed, or the third option is to use synchronous replication, which we will discuss next. If we really want to make sure that the failover will not mean lost data, we can replicate synchronously, but we must keep in mind that this can be expensive. To do this, we must make some changes in the primary database configuration. So, nano temp primarydb PostgreSQL configuration file. We search for the synchronous _commit parameter and we set it to remote apply. What does remote apply mean? Basically, the write requests will wait until the standby replicas have received the commit record of the transaction but also applied it. This way, the last commit becomes visible to the queries on the standby. We should also specify the replicas which are synced using the synchronous standby names parameter. Here, we select all possible replicas. Then, we do a restart on the server. Yet, we forgot to set one important parameter. We need to turn on the wall hints parameter. This is necessary if we want to bring back a failed master. Until now, we discussed how a standby server can be promoted as a master in the event of a failure. But how can the old master be added back to the cluster as a standby without rebuilding it from scratch? We search for wall_log_hints and we set it to on. This parameter will add some extra information to the wall files. After the disaster happens, we can use this extra information and the pgrewind command to bring back the failed master. Please note that this parameter will bring a small performance overhead. After any change in the PostgreSQL configuration file, we should do a restart. The next thing we have to do is to add a failover command which will be executed when the master fails. The failover command can be any script. Here, I prepared a simple example for demonstration. Nano tmp. The script is called failover.sh. our script is just a few lines. It receives two arguments. The first one is the fail node, and the second one is the name of the trigger file. First, the script checks whether it is the secondary node that has failed. If it is, do nothing and exit. For the moment, we don't want to handle standby failures. If the primary node has failed, then we create a trigger file using the touch command. When the trigger file is spotted by the secondary node, it will cause the streaming replication to end, the standby will be promoted, and it will open in read-write mode. As mentioned, Pgpool will call this script when the primary node fails. Still, to achieve this, we need to configure Pgpool. So, nano user local etc Pgpool configuration. We search for failover _ command. Here, I specify the location of the script. Then the first argument, which is the fail node. Note that we have a placeholder here, %d, for the fail node. Then, the second argument is the name of the trigger file. In our case, temp/replicadb/down.trg. This argument will be used by the script to create an empty file called down.trg. Next, we'll see how the replica server reacts to this file. For the automatic failover to work, we have to make some changes on the replica server. We go to temp replicadb to edit the PostgreSQL configuration file. Here, we search for promote trigger file, and then we specify the name of the file we defined earlier in the failover script, tmp replicadb down.trg. This is the file name whose presence ends recovery in the standby. Whenever Pgpool detects a node failure, it will execute the script we specified in the Pgpool configuration and react according to our specifications. In that script, we actually created an empty file called down.trg. The slave system checks every 5 seconds for the trigger file, and when it is spotted, it will turn into the master. Once the failover occurs, Pgpool also treats the second server as the new master. After any change in the PostgreSQL configuration file, we should do a restart. Now, it's time to actually test the failover. We start the Pgpool, Pgpool-n. What if the master database is down? Let's try. pgctl-d temp primarydb stop. In the logs, we see that the health check has failed. Then the failover script was executed. Then we see that the node labeled 1 was set as the primary node. Now, if we connect again to the Pgpool client, we'll receive responses only from the second node. PSQL-P 9999 database Postgres. First, let's show the port. From the port value, it's clear that we are connected to the secondary server. Furthermore, the replica node is now in read-write mode. So, if we execute an insert, it will go to the replica node, as we'll see in the logs. Insert into table 1 a random value, and we see it here. To recap, the sequence of the events is as follows. First, the Pgpool middleware realizes that the master is down, then it executes the failover script. The failover script creates the trigger file in the slave data directory. The slave who keeps pulling for the trigger file notices it, and finally, the slave reboots in read-write mode. Earlier, it was in read-only mode, and completes recovery. In most failover scenarios, there is one issue that needs to be tackled. Assume that the primary server, node 0, is unavailable for some time because of a network issue. Then, we fail over to the secondary server, node 1. After some time, network issues are resolved and node 0 is available again. Now, the application should not connect to node 0. It has missed all the writes that went to the secondary node and will not be up to date. Also, the node 1 is now in a read-write mode and won't be able to accept transactions from the primary. The Pgpool middleware handles this situation as well. The process of restoring the original primary server is called failback. For Pgpool, node 1 is now the primary node. And once we recover node 0, or it came back automatically, we must restart Pgpool with the -d option, which stands for discard, so that it treats node 0 as the primary again. If we restart it without the -d option, it will continue to work with node 1 as primary. However, before we discard the current state, it is really important to make sure that the fail master has been updated with the latest modifications. As we mentioned previously, we can use the pgrewind command to restore the data. In effect, Pgpool ensures that the primary doesn't get written to without anybody noticing it. It does so by recording the status in a Pgpool status file. To ensure that all this works okay, we must ensure that all the connections will go through the Pgpool middleware.